The host developing an ASP.NET Web API for hosting in a traditional ASP.NET application feels very much the same as developing any other ASP.NET MVC application. One of the great characteristics of ASP.NET Web API, however, is that it can be hosted in any process that you designate with hardly any additional work. Example 3-4 shows the code required for hosting our greeting controller in a custom host process, a console AP application, in this case. Example 3-4. A simple web API console host class program. Static void main string args. var config equals new HTTP self-host configuration. New URI http://localhost 50651. config.routes.map http route. Name default API, root template API/controller/ID, defaults new ID equals root parameter.optional. var host equals new HTTP self-host server config. Host.openasync.wait. Console.read press any key to exit. Console.read key. Host.closeasync.wait. In order to host our web API in a custom process, we did not modify the controller and we didn't have to add any magical XML in the app config file. Rather, we simply created an instance of HTTP self-host configuration, configured it with address and routing information, and then opened the host. Once the host is open and listening for requests, we block the main console thread in order to avoid closing the server. When the user chooses to close the host by pressing any key, we close the web API host and exit the console application. Hosting is discussed in greater detail in Chapter 11. Conclusion: in this chapter, we described some of the key design goals behind ASP.NET Web API. We then used the Web API project template to see how the different components that compose the framework are organized and distributed via NuGet. And also to begin to explore the framework's programming model by looking at the default template code. Finally, we wrote our own Hello World Web API and took advantage of ASP.NET Web API's self-hosting abilities. The chapters that follow will drill into each of the topics introduced here and provide a great deal more depth, starting with Chapter 4, which explores the underlying mechanics that make the ASP.NET Web API work. Chapter 4: Processing Architecture. And now for something completely different. The previous chapter presented the core ASP.NET Web API programming model, introducing the set of fundamental concepts, interfaces, and classes exposed by this framework. Before we address the book's core subject of designing evolvable web APIs, this chapter takes a short detour to look under the hood and present the underlying ASP.NET Web API processing architecture, detailing what happens between the reception of an HTTP request and the return of the corresponding HTTP response message. It also serves as a roadmap for the more advanced ASP.NET Web API features that we will be addressing in the third part of this book. During this chapter we will be using the HTTP request presented in example 4-1, as associated with the controller defined in example 4-2, as a concrete example to illustrate the runtime behavior of this architecture. processes controller contains a get action that returns a representation of all the machine's processes with a given image name. exemplifying HTTP request is a get on the resource identified by http://localhost 50650/API/processes, name equals Explorer, which represents all the Explorer processes currently executing. Example 4-1. SAM. PLE HTTP request message get http://localhost 50650/API/processes, name equals Explorer HTTP/1.1 user agent Fiddler host localhost 50650 accept application/JSON. Example 4-2. SAM. PLE controller public class process as controller API controller. Public process collection state get string name. If string dot is null or empty name. Throw new HTTP response exception HTTP status code dot not found. Return new process collection state. Processes equals process. Dot get processes by name and name. Dot select P equals new process state tab. Public class process state. Publicint ID get, set. Public string name get, set. Public double total processor time in millis get, set. Public process state. Public process state process PROC. ID equals PROC ID. Name equals PROC process name. Total processor time in millis equals PROC total processor time dot total milliseconds. Public class process collection state. Public enumerable. Processes get, set. The ASP.NET Web Processing Architecture, represented in Figure 4-1, is composed of 3 layers. The hosting layer is the interface between Web API and the underlying HTTP stacks. The message handler pipeline layer can be used for implementing cross-cutting concerns such as logging and caching. However, the introduction of ONDIS CUSIT in Chapter 11 moves some of these responsibilities down the stack into ON middleware. The controller handling layer is where controllers and actions are called, parameters are bound and validated, and the HTTP response message is created. Additionally, this layer contains and executes a filter pipeline. Let's delve a bit deeper into each layer. Figure 4-1. Simplified.ASP.NET Web API Processing Model. 1. ON hosting support was introduced in ASP.NET Web API, version 2. The hosting layer, the bottom layer in the Web API processing architecture, is responsible for the hosting and acts as the interface between Web API and an underlying HTTP infrastructure, such as the classic ASP.NET pipeline, the HTTP listener class found in the .NET frame, works system.NET assembly, or an ON host. The hosting layer is responsible for creating HTTP request message instances, representing HTTP requests, and then pushing them into the upper message handler pipeline as part of processing a response. The hosting layer is also responsible for taking an HTTP response message instance returned from the message handler pipeline and transforming it into a response that can be processed by the underlying network stack. Remember that HTTP request message and HTTP response message are the new classes for representing HTTP messages, introduced in version 4.5 of the .NET framework. The Web API processing architecture is built around these new classes, and the primary task of the hosting layer is to bridge them in the native message representations used by the underlying HTTP stacks. At the time of writing, ASP.NET Web API includes several hosting layer alternatives, namely self-hosting in any Windows process, e.g., console application or Windows service. Web hosting using the ASP.NET pipeline on top of Internet Information Services (IIS). ON hosting using an ON compliant server, such as Katana 1. The first hosting alternative is implemented on top of WCF's self-hosting capabilities and will be described in Chapter 10 in greater detail. The second alternative, web hosting, uses the ASP.NET pipeline and its routing CA capabilities to forward HTTP requests to a new ASP.NET handler, HTTP controller handler. This handler bridges the classical ASP.NET pipeline and the new ASP.NET Web API architecture by translating the incoming HTTP request instances into HTTP request message instances and then pushing them into the Web API pipeline. This handler is also responsible for taking the returned HTTP response message instance and copying it into the HTTP response instance before returning to the underlying ASP.NET pipeline. Finally, the third hosting option layers Web API on top of an OAuth-compliant server. In this case, the hosting layer translates from the OAuth context objects into a new HTTP request message object sent to Web API. Inversely, it takes the HTTP response message returned by Web API and writes it into the OAuth context. There is a fourth option, which removes the hosting layer entirely. Requests are sent directly by HTTP client, which uses the same class model, into the Web API runtime without any adaptation. Chapter 11 presents a deeper exploration of the hosting layer. Message handler pipeline. The middle layer of the processing architecture is the message handler pipeline. This layer provides an extensibility point for interceptors that addresses cross-cutting concerns such as logging and caching. It is similar in purpose to the middleware concept found in Rubus Rack, Python's WSGI web server gateway interface, and the Node.js Connect framework. A message handler is simply an abstraction for an operation that receives an HTTP request message instance and returns an HTTP response Sage HTTP response message instance. The ASP.NET Web API message handler pipeline is a composition of these handlers, where each one except the last has a reference to the next, called the inner handler. This pipeline organization provides a great deal of flexibility in the type of operations that can be performed, as depicted in Figure 4-2. Figure 4-2. SEH handler processing examples. The diagram on the left illustrates the usage of a handler to perform some pre- and post-processing over request and response messages, respectively. P. Processing flows from handler to handler via the inner handler relationship in one direction for request processing and in the reverse direction for response processing. Examples of pre- and post-processing are changing the request HTTP method, based on the presence of a header such as XHTTP method override, before it arrives to the controller's action. Adding a response header such as server. Capturing and logging diagnostic or business metric data. You can use handlers to short-circuit the pipeline by directly producing an HTTP response, as shown on the right side of Figure 4-2. A typical use case for this behavior is the immediate return of an HTTP response with a 401 unauthorized status if the request isn't properly authenticated. In the .NET framework, message handlers are classes that derive from the new HTTP message handler abstract class, as shown in Figure 4-3. Figure 4-3. Message handler class hierarchy. The abstract sendAsync method receives an HTTP request message and asynchronously produces an HTTP response message by returning task. This method also receives a cancellation token, following the tap task asynchronous pattern guidelines for cancelable operations. The message handler pipeline organization just described requires a data member to hold a reference to an inner handler as well as data flow logic to delegate requests and response messages from a handler to its inner handler. These additions are implemented by the delegating handler class, which defines the inner handler property to connect a handler with its inner handler. The sequence of delegating message handlers that constitute the pipeline is defined in ASP.NET Web API's configuration object model on the HTTP configuration.message handlers collection property, e.g. Config.messagehandlers.add new trace message handler. The message handlers are ordered in the pipeline according to the configure message handlers collection order. ASP.NET Web API 2.0 introduces support for the OWIN model, providing the OWIN middleware as an alternative to message handlers as a way to implement cross-cutting concerns. The main advantage of OWIN middleware is that it can be used with other web frameworks, e.g., ASP.NET MVC or SignalR, since it isn't tied specifically to Web API. As an example, the new security features introduced in Web API 2.0 and presented in Chapter 15 are mostly implemented as OWIN middleware and reusable outside of Web API. On the other hand, message handlers have the advantage of also being usable on the client side, as described in Chapter 14. Route dispatching at the end of the message handler pipeline. There are always two special handlers. The routing dispatcher implemented by the HTTP routing dispatcher class. The controller dispatcher implemented by the HTTP controller dispatcher class. The routing dispatcher handler performs the following. Obtains the routing data from the message, e.g., when web hosting is used, or performs the route resolution if it wasn't performed previously, e.g., when self-hosting is used. If no route was matched, it produces a response message with the 404 not found HTTP status code. Uses the route data to select the next handler to which to forward the request, based on the matched if route. The controller dispatcher handler is responsible for using the route data in a controller selector to obtain a controller description. If no controller description is found, a response message with the 404 not found status code is returned. Obtaining the controller instance and calling its execute async method, passing the request message. Handling exceptions returned by the controller and converting them into response messages with a 500 internal error status code. For instance, using the HTTP request of example 4:1 in the default route configuration, the route data will contain only one entry with the controller key and process ES value, T. This single route data entry is the result of matching the http://localhost 50650/ API/processes, name equals explorer request URI with the /API/controller/ID route template. By default, the routing dispatcher forwards the request message to the controller dispatcher, which then calls the controller. However, it is possible to explicitly define a parent handler, as shown in Figure 4-4. Figure 4-4. P. Are route handlers in the route dispatch handler. In this case, the request is forwarded to the handler defined by the route, not to the default controller dispatcher. Reasons for using per route dispatching include flowing the request message through a route-specific handler pipeline. A concrete example is the use of distinct authentication methods, implemented in message handlers, for different routes. Another reason for using per route dispatching is the substitution of an alternative framework for the Web API top layer controller handling. Controller handling the final and uppermost layer in the processing architecture,